In the last series of videos, I showed that you can do stoichiometry with pressures when the volume and temperature are constant. In this video, I wanted to take a look at doing stoichiometry with volumes when the pressure and temperature are constant. So let's just note here, 6-liter container of nitrogen, 2 atmospheres, hydrogen, 2 atmospheres, and then a final mixture at 2 atmospheres. So you're starting with 2 atmospheres for one reactant, 2 atmospheres for the other reactant, 2 atmospheres for the final reaction vessel, constant pressure. And you'd get that by having a reaction vessel that's flexible. It can change volume without changing pressure. And then in this case, we've got 25, 25, and 25 degrees Celsius. So we have the pressure and the temperature constant, and our number of liters, our volume, is going to change. And that allows us to do this bit of comparison that may look familiar from our last video. We need moles in general for stoichiometry. In this case, our moles is going to be proportional to our volume. N moles, that symbol is proportional to, and then V for our volume there. And I'll just very, very quickly skim through how that looks once again. PV equals nRT. And in this case, if we want to solve for N will equal PV over RT. But if your pressure and temperature and R are constant, you can say that N is going to be equal to times P over RT, where pressure is constant, R is constant, T is constant, and then N is directly proportional to V. And again, in reverse, you can turn a proportionality sign into an equality by adding a constant. That's our constant there. So based on this, we should be able to do our stoichiometry with volumes, just like we did stoichiometry with pressures in the previous video. Important stuff. Let's get down to the stoichiometry. We'll start with what we have. And as we did with the previous video, we used pressures. Now we're going to use volumes. I have 6.00 liters of nitrogen, and I have 15.0 liters of hydrogen. I've got my balanced chemical equation over here. 1 nitrogen, 3 hydrogens for every 2 NH3s. Normally we'd say moles and moles and moles, but now since our pressure and our temperature are constant, we can say volumes and volumes and volumes. So let's take care of this stoichiometry over here. We have a 1:3 ratio. For every 1 liter of nitrogen, there's 3 liters of hydrogen. For every 3 liters of hydrogen, there's 1 liter of nitrogen. Which means we need 18 liters of hydrogen and 5 liters of nitrogen. And we have our limiting reactant and our excess reactant. Have 6, need 5, that's more than we need. So that is our excess reactant. Have 15, need 18, we don't have enough, that becomes our limiting reactant. Once again, the big difference here, normally stoichiometry we'd get moles, but if PV equals nRT, we can get a proportionality between moles and volume, and then we can do our stoichiometry with volumes. In short, this is different because we're using volumes to do the stoichiometry instead of moles. We're going to get the same stuff we normally get. Now that we know what we need, we can get an amount excess. And we're just going to subtract what we have of our excess reactant, that is 6.00 liters, minus what we need, 5.00 liters, and that is of the nitrogen. And so we have 1.00 liters of nitrogen excess. And that is an important number for us. Let's take a look at our theoretical yield. It's going to be based on our limiting reactant. We have 15 liters of that hydrogen gas. And from our balanced chemical equation, we know for every 3 liters of the hydrogen gas, there's 2 liters of ammonia, NH3. So our theoretical yield is 10.0 liters of hydrogen gas. With the pressure problem, we used Dalton's law of partial pressures and just added the 2 partial pressures directly. In this case, we can add our volumes directly. And we can get a total volume, and that is what we want, our total volume, by adding our volumes together. So we can take V total as the volume of our excess nitrogen and the volume, oops, that should have been NH3. Sorry about that. NH3 there, if I had watched my dimensional analysis. NH3, in this case 1.00 liters, and 10.0 liters gives us 11.0 liters as our total volume. We might as well highlight that in some meaningful way, because it is our answer. That made it look worse. There we go. So what I want to do now is do it the long way, the hard way. And if this is okay with you, you can just stop the video.